Alright, so want to do a little introduction to energy. It might turn into more than an introduction, just kind of depends on how long this video gets going and of course how carried away I get. But we're going to talk about work and energy. We've talked about how we can have things move, and we've done force and kinematics and all that stuff. And if you were really spectacular at math, you should be able to do quite a lot with those. Um, but eventually they get to be too cumbersome. They get to be very difficult, and they're all vectors and things like this. So we want to switch over to talking about energy now, and especially because physics is the study of energy ultimately. It's what it turns out to be. And so we're going to start getting into that now. So what we want to do is I'm going to give you my own definitions of energy and something else called work that's very closely related to it. Uh, so the best definition I know of, simple, covers everything. Definition for energy is ability to do work. You think, well, okay, what is work? And I don't mean this work as in you're working on your homework, although this kind of work is involved in that. This is the physics kind of work. And then we can define work, just so you have this total complete definition of it, as a transfer or change in, but mostly a transfer of energy. And I know what you're thinking. You're thinking, oh my gosh, these two things, I just defined them with each other, and so it's kind of cyclical. But the more you think about it, this will kind of make sense. So energy is just your ability to do stuff. It's your ability to do work, which is being able to do something. And work, when you do work, you're actually transferring that ability from one object to another. So if you go and you push a heavy box, what you're doing is you're giving your energy to that box. You're transferring it over to that box, so that box now has the ability to move. So you walk up and you have, say, a box that's sitting on a frictionless floor, and you push it. Well, you just did work on that box. You transferred some of your energy that was from the food you ate before, chemical energy, into that box through your muscles, and now that box has the ability, it could go slide across the room and hit a ball, and then the ball could start moving, and it would transfer now its energy to that ball. So work is just a bunch of stuff transferring energy between them, transferring energy back and forth, and energy is just when you have energy, then you can do that. You can transfer that energy to other things. You can do work on them. You can give them your energy. Both of these things, since they're so closely related, have the same units. Okay, the unit ends up being called a joule. It's a J, and it is a Newton times a meter, and we'll talk about how that comes about in a little bit. Both of these things are scalars. They are scalars, and so that makes them a lot easier to work with than the vector stuff we've been doing so far. So let's start by defining mechanical work. This will be a big focus for us. Mechanical work, and this is defined as essentially, this is just work done by a force that's parallel to the displacement of the object. So work done by a force, right? The force, and I'm going to use the little parallel sign, by a force that is parallel to the displacement. Sorry, I wish I had better handwriting for you. So essentially, if you push on something, then this is your mechanical work. That's kind of our definition of it. It's just you're pushing on it, and it's in the direction that it's actually moving. And we'll come back to this again when we talk more about work, and I'll give you a little more information on that. So let's talk about energy. What kind of energies have? Well, there's all kinds of energy. There's energy due to things moving, there's energy due to things position, there's chemical energies, there's all these kind of energies. And the two we're mostly focused on that we're going to really dive down into, and not kind of just say, oh, well, let's just whatever amount of work, whatever amount of energy it was for chemical energy or something like that. The first one is kinetic energy. Kinetic energy, and if you're thinking back to where we talked about kinematics, where it was we were studying motion, then you have a pretty good idea. This is the energy due to motion of an object. So any object that is moving will have kinetic energy, and this kinetic energy, you can write it a few ways. You can write E sub k, or you can write KE, or even in some places it's a capital T. You're not likely to see that at this level, but it could be just a capital T. That happens later. I've seen that. But ultimately, it's defined as 1/2 the mass of an object times its velocity squared. That makes it a scalar. We have a velocity squared. If the velocities were negative, they'd become positive. We lose all information about direction here, and mass is a scalar, so this thing becomes a scalar. If you look at the units that you would have, this would be a kilogram. This is a meter squared per second squared, so it would be a kilogram meter squared per second squared. Well, if you think back to what a newton was a kilogram meter per second squared. And so this is a kilogram meter per second squared times a meter, which is a newton times a meter. So that gives us that same unit that I set up here were the units for this. So that's kinetic energy. It's pretty simple. If something is moving, it has this. It can have both linear kinetic energy, which is this one here we're interested in, but it can also have rotational kinetic energy, which is something that we'll talk about later, where it's ultimately just a form of this linear kinetic energy. It's just, turned into rotational version of it. And then the next one we have is potential energy. Potential energy. And this is essentially energy that's stored in a system due to its position. So it's energy stored due to position, how everything is arranged. So an easy example of this is a stretched rubber band. The position of all the particles, all relative to each other. You have that rubber band stretched. No actual energy or work is being done, but if you let that rubber band go, you let it contract and go back together, then it's gonna turn itself into kinetic energy. It's gonna turn itself into other types of energy. So this is energy stored in something. This is the same thing of if you have a compressed spring. So you push down on a spring and you compress it. If you let it go, it's going to spring back up, like the shocks in your car. This could also be if you're holding a ball up above the ground. If you let it go, then it will drop and fall down. But while you're holding it up in the air, it has that stored energy due to its position where it is. Okay, and so in the examples I just gave, those are the two types we're worried about. The first is gravitational, so gravitational potential energy. Gravitational, I'll spell it right eventually, and with my handwriting it doesn't matter if I spelled it right because you can't read it. I probably should have told you up here, the unit usually used for this is sometimes it's E sub P or PE, or even sometimes a V or a U. You might see a U, so I'll go ahead and put that one in a capital U. But this is going to be equal to a few different things depending on which kind it is. So for gravitational, this potential energy is equal to, if you're near Earth's surface, m times g times h. This will actually be kind of important where this comes from, but at the moment it's m times g times h. So you look at how high something is above wherever you set your 0 point to, and you calculate it. Now the one thing you have to keep in mind is these potential energies, they're position based, but positions are relative to the coordinate system you choose. So for example, if I hold a ball right here, well, if I choose this as my 0 point, then I'd be basically saying that this has no potential energy. But if, say, the ground, or let's say I have a table here, right? I have some table sitting here, and I choose the top of the table as 0, well then, now this would have a potential energy based on whatever this height is from the table. But if you took and moved the table out of the way, then my potential energy, I could redefine, I could say the ground now is 0, then the potential energy might be based on coming from the ground. So since we can always just seem to arbitrarily change how much potential energy something has by just picking where we set our coordinate system axis, right? I can call this 0 or this 0 or this 0, or I could dig a hole in the ground, or even if I didn't dig a hole in the ground, I could come down below the ground and set the zero position here and measure it from there. I could put the zero position above the ball and measure. I mean, there's anywhere I can do literally an infinite number of things. So how do we actually even agree on this? Well, one, we can all just agree on the zero position, like call the ground zero, which tends to be kind of a convention that you do. Although doing that doesn't make the problems that you work out in these necessarily the easiest. You basically want to pick a position where something is zero, and it cuts some stuff out of your equations that you've built up. But in doing that, then it looks like you would have a different answer than anybody else. So when we talk about potential energy, you never really want to just talk about potential energy, like the potential energy of a single point. Because if we just say, what's the potential energy of the ball right there? Well, then it depends. It could be a negative potential energy, it could be a little positive one, a bigger positive one, or a gigantic positive one, depending on where you put your 0 point. What you want to do is always talk about the change in potential energy. Then it becomes consistent. Then we all agree on it. Okay, if we talk about the change in it, so then it doesn't matter if I choose whatever it is. If we talk about change, then I can say, what's the potential energy between the ball and the top of the table? Well, then that doesn't matter. If I set this as 0, then this would be something like -5, and then the height would be -5 minus 0, and its potential energy change as it went from here to there would be based on -5. And I could do something different. I could choose this as 0, in which case this is -5 and this is -10. And then if I look at the change in the height for the change in potential energy, then it's -10 minus -5, and it still becomes -5. And I could have set this as 0 down here, in which case this is 5 and this is 10, and my change in height that I'm interested in between these two is 5 minus 10, which is again -5. So if we're looking purely at change in potential energy, then we can all agree, assuming we're not changing the mass or the acceleration due to gravity, so this has to be near Earth surface, then it's just a change in height, and then it becomes more like a displacement, in which case no matter what coordinate system we pick, it's always going to be the same change in that rather than just what it is at a single point. In fact, you can't even talk about what it is at a single point without at least glazing over and ignoring that you have actually defined it relative to some 0 point. Like if we just do MGH, this is just assuming the ground or however far it can fall down is 0, and so it's technically MGH minus 0 where we're saying the ground is 0. Okay, so just kind of keep that in mind. Think about it some, and it should make sense. The other kind of potential energy we have is elastic potential energy. Elastic. And this is kind of like what I was talking about with the rubber band or the spring. So if you have a spring will have something called a spring constant, K. And this essentially, this K, spring constant, this K, it basically tells you how strong or how stiff this spring is. The bigger K is, the harder this spring is to bend or stretch. Okay, its units would be in a what does that have to be in? So it comes from this equation. Sorry, I'm kind of having a moment here. It comes from this equation called Hooke's law, which we're going to study later. It's the force on a spring, and then if this is x, this is a Newton over here, which is a kilogram meter per second squared. Over here, this just has a meter, so the kilogram and second squared have to come from this constant. So it's a kilogram per second squared would be the units for it. Sorry for forgetting that real quick. Thanks for letting me work it out. It's going to have a unit of a kilogram per second squared, so unit of kilogram per second squared. That's your unit for that thing, your spring constant. And then if you have an object attached on here, the potential energy, then this position here, if it's unstretched, is called equilibrium, where it's unstretched, you haven't stretched or compressed the spring at all, and then you measure everything either forward or backward from there, and then how far you go either to the left or to the right is called its position, x. So x to the right or x to the left, and we're going to not even worry about whether or not that's a positive or negative, and you get you get energy potential elastic, that could be, or potential energy sub E, something like that. And it's 1/2 the spring constant times the amount it's stretched or compressed squared. So it's very similar to kinetic energy in form 1/2 mv squared versus 1/2 kx squared, if that helps you remember it at all. But these two are our potential energies and that we're really interested in, and this one is our kinetic energy that we're really interested in. Are there other kinds of energies and potential energy, other kind of potential energies, things like that? Yes, there's potential energy between atoms and things like that, and there's electrical potential energies and all kinds of stuff. The strong force could have potential energies. Any kind of fields that you have can have a potential energy to them. Gravitational, electromagnetic, strong force, weak force, all these kind of things, which we'll learn about later, they all have the potential to do work. Your potential energy here, it's your potential to do work, and so they all have that kind of potential energy stored in them. Okay? Now let's talk more specifically about work. Okay? Work itself. We define the work as a transfer of energy, right? So let's define it a little more mathematically. So work, let's define this more mathematically. We're going to use this capital W for it, and we're going to fully define it using something called the work kinetic energy theorem. And it is simply a statement that work is equal to the change in kinetic energy of an object. So the work done on an object, you look at its change in kinetic energy. That is pretty much it. You can do this macroscopically on large scale things, or microscopically, in which case we would call this heat, where you would transfer and the atoms and molecules inside an object would heat up and they would vibrate a lot faster, and that's just a form of kinetic energy. And then if we wanted to come up with some other ideas, we can also even calculate work, not just through change in kinetic energy, which, by the way, of course, would be 1/2, assuming the mass stays the same, 1/2 mv final squared minus 1/2 mv initial squared, kind of a thing. So 1/2 m delta v squared would be, the change in kinetic energy. If the mass is changing, of course, then but we haven't really learned about changing mass so much yet, but we will, towards the end of the course. But right there, 1/2 mv squared. The next little part of this is how can we actually calculate this? And I'll give this to you right now. You probably haven't done calculus yet, but if you have, then the actual way you calculate this based on forces is the integral of f, vector f, dot, that's a dot for dot product, dot dl or dx or dt, or not dt, but dl, dh, d something, some distance. And this can reduce down to something pretty good. If you know anything about dot products multiply two vectors together, and they eliminate any, and they basically multiply together components that are parallel. So this only multiplies the parallel parts together, and so we can reduce this to simple situations where this isn't along some curvy path with a varying force or anything like that. If we have a constant force, we can just do F parallel to displacement. So F parallel to displacement, multiplying those together. Vectors again, but it ultimately gives us a scalar. And then if they are parallel to each other and you have the angle between them, this becomes F d cosine theta. I believe that's the way it will look in your data booklet, or usually when you find it in books it looks like that. And I'll show you why this is, because dot products can be expressed this way. So if we had some object sitting on the floor or something, some box or something, and we were going to push it, and we took and we applied a force to it at an angle, right, at some angle, and this was our force we applied to it, and we knew that the box was displacing, moving along the floor, so we pushed it for 5 meters or whatever, some distance that we pushed it across the floor or pulled it across the floor with this force. What would be the work that we did on it with this force, or what would be the work that this force did on it? It could be a rope pulling it or something like that. Well, if you look at this thing, you've got a force that's parallel to that displacement. This would be that F parallel I was talking about. And then you're going to have a force that's perpendicular to it. And if you think about this, this would be the force that's perpendicular to it. Now, if we're assuming this box is only moving in the direction d, it's not moving up or down, then this force here is basically lifting up on it, but it's not actually changing the box at all. It's not moving it in any direction. It's not lifting it up off there. It's not crashing down through. So this force here is almost just being wasted. It's not actually contributing to the motion of the box. The only part that is actually contributing to it, that is actually moving at this distance d, is this parallel force here. Okay? And if you calculate this parallel force, if this angle is theta, then this parallel force is equal to F cosine of theta. It's the parallel component. And that's what I mean by this. Take the parallel component of the force and multiply it by this displacement. And notice you end up getting this. Just a little rearrangement. It'd be F cosine theta times d, or just FD cosine theta. But that's where that cosine comes from. You're taking the parallel component of the force that's parallel to the actual displacement that's occurring, because anything perpendicular isn't contributing to that motion. Remember, perpendicular stuff doesn't contribute at all. Those vectors are independent from each other, linearly independent. So it doesn't contribute at all, and this is the only part you're worried about. So why do I prefer this version over this version? Well, imagine you were doing this problem and you weren't given that angle there, but you were given this angle up here, whatever it happens to be, theta 2. I'll change it, make it a little different. This is theta 1. But what if you were given this one? If you're given this vector, this angle up here, well then in that case, this would be F, this is F cosine theta 1, but what would it be with theta 2? It'd be F sine theta 2. So I prefer this one because you don't always just, you're not always given the angle that's between the force and the displacement. You might be given an angle between the force and the perpendicular to the displacement, or something like some other angle, and you have to be able to go in and find, it might actually be the sine. You have to be able to just find that component and then do it. So it's F, the component of F parallel to displacement, multiply them together. You don't have to worry about doing dot product by taking the parallel component. You are essentially doing the dot product just in a roundabout way, and then multiplying them together. Okay, so this here, we'll rewrite it just once for you. Work is equal to, I like to remember F parallel to D, but in your data book, look at and stuff like that, it's going to look like FD cosine theta. But you have to remember this has to be the angle between F and D. So use either one you want, whichever you're more comfortable. But if you're given an angle that's not between F and D, then you're going to have to convert it to the angle between F and D, or just use my version here. And you know I'm a big fan of learning one thing and that being it. Now, looking at this, what would happen if I had a force, so let's say I had this here, and let's say I had some other force opposing this motion, which could be something like friction, or this could be a tug of war. You're pulling the box this way, so we can call this F1, right? F1 on all of these, F1 parallel. And we had some other force trying to oppose this motion, and it was losing. It's pulling this way, but the displacement is in the opposite direction. Well, if you do that, you're going to end up getting a negative value for work. And I know what you're thinking. You're thinking, well, hey, you've told us that you've told us that negative and positive values just tell you direction for vectors. And here we are with something that I told you was a scalar, and now we have a situation where we can get a negative out of it. And the short answer to that is the difference between scalars and vectors is a little more complicated than we try to make it out to be at this level of physics. They're actually both what are called tensors, and we can have a negative scalar, and it is kind of a negative type direction, and you can have positive work and negative work. Positive work is going to occur when the force that is being applied is in the same direction as the displacement. Negative work is going to be when the force being applied is in the opposite direction of displacement. And you're going to have to pay close attention to this. So if I'm lifting something up into the air, I am doing, the work being done by gravity on it is going to be negative because gravity is pulling down on it, but its displacement is up. But if I drop something down, then the work being done on it by gravity becomes positive because the displacement is down and gravity is pulling it down. So just pay close attention to that, whether or not different works are positive or negative. They can also lead you to paying attention to, positive negatives can also lead you to paying attention to a key difference here of, you'll see some problems, work done on something and work done by something, right? And you have to pay close attention to these because these are different things. And sometimes this positive negative is going to come into play whether you're talking about this. So let me give you an example. If I had a ball, all right, and here was the ground, and I lifted this ball up at a constant rate, so I didn't change its speed, right? I didn't change its speed. I lifted it at a constant, whatever speed it was, and I lifted it a distance. That was supposed to be the same ball there, sorry. We'll make it a strike ball, look like a strike ball. I lifted it at a constant speed, over a height h, a distance d, whatever it is. We lifted it at a distance d. Then there's two questions that you could likely be asked. The one question you could be asked is, what's the work done on the ball? Well, if you think about this, in terms of the work kinetic energy theorem, if I'm lifting it at a constant speed, well then the kinetic energy is not changing at all. And by definition, that means that the work done on the ball is zero. So the work done on the ball here would be zero. The work done on the ball. That's a little word on there. Work done on this ball is zero. You could also think that if I did the net force on this thing, if it's not accelerating constant v, then the net force on this thing is zero. And any work that you do lifting it, which would be a positive force that you're applying to it, that gives you a positive force. Well, then gravity is doing, the mg force here is going to exactly cancel you out. It's going to do the negative version of whatever you did, because this force is equal to this force, and they're both applied over this distance, except this force times this distance gives you a positive work. This force times this distance gives you a negative work. And so they exactly cancel out. And again, the work done on the ball is zero. Okay? And you don't have to do individual forces. You could just do net force on the ball, which not accelerating. The net force is zero. So net force of zero times any displacement is zero work. But if I asked you the question, what is the work done by gravity on the ball? All right, this keyword by instead of on. On is like the total work done on it. The work done by an individual force. Well, then in that case, you would get that the work is equal to negative mg, that's the force of gravity, times d, right? D in this case would be equal to its change in height. Mg, change in height, which is essentially just, if we're just keeping those the same, this is just negative, because it's in the negative direction, negative change in potential energy. So the work done in raising a ball, and here it might not always be a negative thing that it turns out to be. It was just in this case because this is a negative work. If the ball was going the other way, if we were dropping it back down, then this would be a positive. So, kind of you almost ignore that and just think about situation by situation about whether or not that should be there. It just happens to be in this situation is there. But essentially, the work done lifting something, the work done by gravity, is a change in its potential energy, either positive if it's dropping, positive is being raised, or negative is dropping. If it's being raised, we're getting more potential energy, right? So this would be you'd have to pay attention to this. Delta H would make this become back to positive, but it would raise it up, and we would gain potential, because dropping something from 10 feet in the air, it's going to go faster when it hits the ground than dropping something from 1 foot in the air, which means bigger change in kinetic energy. It's going faster when it reaches the ground if you drop it from higher. It gives you this here. Now, another interesting thing about this is all path independent. Okay? If we're just talking about forces that don't create any heat, these are called conservative forces, then this stuff is path independent. So that means that if you go to that wavy slide at the fair where you get on the little carpet that reduces your friction, so we assume the friction is zero, and you get on this little carpet and you go down it, that you're going as fast when you reach the bottom of this thing, right? You're going as fast when you reach the bottom as you are if you just jumped off over here. Because this work being done here on you is independent of all this direction. And it may take you longer to reach the bottom, but by the time you reach the bottom, the same amount of work would have been done on you by gravity, and you'd have to have the same change in kinetic energy. So the V final here, like is equal to the V final here. And I'll come back to this example too when we talk about this later. Like for one, why is it then if you go down the slide, you're safe at the bottom, but not if you jump off the back? Well, if you think about it, you should come up with the answer of why jumping off the back of the slide, you're going to break all your bones in the hospital and maybe end up getting yourself killed. Whereas going down the slide, you reach the bottom, you're perfectly fine, you're unhurt. So if you think about that, and especially why I put these magnitude signs around these velocities here, you should be able to come up with the answer of why it's safe to go down this way. But you end up with the same velocity. And that brings us to another point, which is conservation of energy. Conservation of energy. Energy, Solomon said, cannot be created or destroyed. It can only be changed, which means we can only transfer it around from object to object. At least I should say it is locally conserved. If you think about this in the grand scheme of things, what we mean here is that if I have a certain amount of energy inside a box, right, it has a certain amount of energy stored inside the box, however it could be kinetic, potentially it could be things moving around. The energy in this box cannot be reduced without that energy that it reduces by actually passing through the surface of the box. It has to actually, that means it can't be here and teleport over here without passing through the box. So it's a local conservation. Now I'm pointing this out because there may be things in the universe that are conserved, but they're not locally conserved, in which case they're not much use to us because we'd never know of it. But it could be something like temperature. We can, temperature, we can change the temperature without changing the energy and having energy go through the box. We'll talk more about that later. But maybe it's conserved throughout the whole universe. Okay, maybe if you reduce the temperature here, that temperature over here has to go up by the same exact amount, and it's not locally conserved, but it is conserved over the whole entire universe. I'm probably just babbling here on about it, but my point is we really only know about locally conserved things. We can't say things about other things definitely not being conserved because they might be conserved non-locally. So this is a local conservation. I keep trying to say conversation. So it's locally conserved. What we can do here is talk about, well, if we have our net work done, this could be change in our chemical energy, so chemical, plus our change in kinetic energy, plus change in potential energy, plus something called heat, which we haven't talked about, plus any other energies you have. All of this adds up, and it's the total work you've done. It's your net work, and this kind of thing is basically telling us that all of these things added up get conserved in whatever work was done. What we're interested in now is something called mechanical energy, and similar to, well, it's kind of similar to the energy we talked about before, the mechanical work I defined before, but basically this is the sum of all kinetic and potential energies of a system, okay, macroscopically, not microscopically really. Well, ultimately, if we go microscopically, then we can do that. But it's the sum of all of these things. And this type of energy, this mechanical energy, sometimes you'll see people listed as ME, capital M, capital E. This sum of all of these things, that equals your mechanical energy, okay? And this is conserved. It's conserved in that you can say the change in mechanical energy is 0, or you can write it as mechanical energy initial equals mechanical energy final. And so the idea here is find all the mechanical energies you have before, all your kinetic and potential energy before, and then you look at the end of everything that happens. You let everything happen that needs to happen, and the sum of all your mechanical and potential energies is now is conserved there at the end. They'll be equal to each other. This only works for things with conservative forces, which means there's no friction or heat loss ultimately. Okay, and we'll do some examples of that later. And you need to remember one thing, that friction does work. So if friction is doing work, it's creating what's called heat, and it does work. You can even do friction times displacement. It's always a negative work. It's always opposite to the displacement. But friction does work too, and if friction is involved, we can't conserve mechanical energy, but if you can take into account heat and all the other kinds of energy that could get produced, then you can conserve it. But here we use this mostly when it's ignoring any heat loss. Okay, so we're really interested in conserving this. The last couple things is the rate at the rate at which work is done, and we call that power. P-O-W-E-R, power. This is in the units of what are called watts, which is just a capital W, which is just a joule per second. Okay, a joule being our energy thing, and so power, capital P, is equal to work over time. It's the rate at which you can do work, so divide by time. So that's our main equation. You can take it a little further and say that work is force times distance over time, and distance over time is velocity. So another alternative form is force times velocity. That works just as well. That there are situations where that will be very useful. And that is power. It's the rate at which you do work. So we'll do some stuff with that too. And then the last thing is the efficiency of something. Efficiency, right? The efficiency in which something does work. And this is essentially equal to useful work slash energy slash power over the total work slash energy, writing it quickly, slash power. It's basically what you get out over what you put in. So the energy put in over the energy output, or the power in versus the power that you get out of it for useful stuff. And I mean like useful, like where I'm actually getting something where it's not being wasted. So wasted stuff would be like heat was created and things like that, where it didn't actually help us meet the goal we were trying to get. All right?